Okay, so this is Calc 2, Lecture 31, Infinite Sequences and Series. Let's continue with the integral test. The integral test was like this. If we are given an infinite series an, if we can find a continuous positive and decreasing function fx such that an equals fn, then if this integral is convergent, then sigma in is convergent, and if this is divergent, then sigma in is not divergent. So that's why it's called the integral test, because we can test the convergence and divergence of this using this improper integral, which is well, it's easier to calculate if the function is nice. Now, when we use it in fact in this form. So the most important application is this. So okay. So I'm not if n is less than 0, it means that it is n to power some positive p, in fact, in the numerator, and that is divergent. So let's assume that p is bigger than 0, so we really have 1 over n to power p with p positive. Okay, so we can find, so the function x equals 1 x to the power p, in fact, does the job. So fx is what? Is continuous, is decreasing, and is positive. For x bigger than or equal to 1. Right? Up to infinity. Okay, so let's look at this integral, the integral 1 over xp dx. Okay, so we have to look at this integral 1 infinity 1 over xp dx, and we just need divergence or convergence, that's it. So let's go back to improper integrals. Remember, this is what? This is convergent if p is bigger than 1, and divergent for p less than or equal to 1, and remember this should be bigger than 0. So, what does it say? It gives us a procedure for this. So this gives me something which is similar to this, and that is for the sigma an. N can start anywhere. N can start anywhere, but I will explain. So let's start with 1, because usually it starts at 1, but anyway, so this is convergent. Oh, so not an. 1 over n to the power p. Right. So it's convergent if p is bigger than 1, and divergent if p is less than or equal to 1. So sometimes we call this thing the p series test because of this p which is fixed for every one of them. So examples that I discussed, I guess I started with one of these series, and that was 1 over n squared. So as an example, examples are so 1 sigma convergent to sigma m. Now what is this? Square of n. So that is, I told you never ever use radical. You might write it at the beginning, write it as exponent. Write it as exponent. That is n to power 1/2, right? So p is between 0 and 1, so it is less than or equal to 1. So this is divergent. So, okay, so that is how this is used. Now, there's another thing which this idea can give us, and that is, well, let me erase this and go back to. So I had this, remember I had this decreasing function that starts at 1 and f at 1, so this is f at 1, okay, so this is f at 1, which is a1, 2, f at 2, which is a2, remember, so 3, that is f at 3, which is a3, and so on. Now I can do two things here. In fact, that's how I proved that 1 over a squared is convergent and 1 over n squared is convergent and 1 over n is not. This is just for any a I or ak. So if I go this way, you see, remember what I did? Now the area under this curve, let me, well, I don't have any other color, in fact it doesn't show if I use any other color. So, the area under this curve, which is like this, right? So, it goes like this, comes down, nothing here, and goes on. Now, it's not curved, but it's some graph. So, let's not write curve, because when you say it's not curved, so get confused. So, graph. So, this graph the area under this graph is what? So, area under is 1 times a1 is 1 times a1 plus 1 times a2 plus 1 times a3 plus dot dot dot. So basically it is sigma a n from 1 to infinity, right? So this area is sigma an. Now what happens to this area? Let me erase this area under the curve from 1 to infinity. So, I should write this thing. So, area under the curve, which is fx, is area under graph of fx. So that is from 1 to infinity, fx dx. Now which one is larger? But definitely, if I remove this, you see this small portion is simply A1, right? If I remove this, area under the graph is larger than area under this thing starting at 2. So one thing that I can say is that one result is that sigma an, if n starts at 2 to infinity, then this is less than equal to the integral. Okay, less than the integral. So if I add a1 to both sides, I can start at 1, and this is a1 plus integral 1 to infinity fx dx, right? So that's one result. Now let's erase this and go the other way. In fact, that's again how I proved 1 over n is divergent. So I go this way this time. And so on. So I'm talking about the graph under this dotted, say, graph. That's graph of something. So say piecewise defined function. Okay, so area under this new graph here. Area under this new graph is 1 times the same thing, right? It's interesting, that's the same thing. 1 times a1, or this is a1, which is f of 1. This point is a2, which is f of 2. This point is a f of 3, which is a3, and so on. Okay, so these are these points. So area under this one is again this thing. Now what's the relation between this area and that area? That one is the same. So what's the relation? You can see from this picture at least that since this is decreasing, and decrease then goes to 0, so it's in a sense it's not increasing going up and down. So if we're being decreasing this way, it makes it say concave up. So I can say that this integral definitely from 1 to infinity fx dx is less than this sigma and from 1 to infinity an. Right? So what does this mean? Let me erase the graph and look at these two results. Put them together. So, on one hand, let me write this in the middle, an, n from 1 to infinity, and this is bigger than 1 infinity fx dx is less than a1 plus 1 infinity fx dx. Okay? So, okay, so this is in fact one of the interesting things that we can find. This basically gives me an idea on how this thing is. So it gives me this, whatever I call it, S. So it tells me that S is a number between these two. And this integral. Right? for example, I can for example, for sigma 1 over n squared, and from 1 to infinity, let's say this is s, then s is between integral from 1 to infinity 1 over x squared dx. And what is a1? a1 is simply 1 plus integral 1 to infinity 1 over x squared dx. Okay, now what is this integral? You know, we have found it a million times. So this is 1. You can find it, we did. This is 1 in fact, so this whole thing is 2. So we have s is bigger than 1 and less than 2. So we have found a bound, or two bounds in fact, a lower bound and an upper bound for this sum. Finding bounds, upper and lower, is crucial in mathematics, and I mean many people just do research on making this bound smaller. So making this bound, if I could say prove that it is between 1.2 and say 1.8, for example, that would be a much nicer bound. And in fact, it might, finding a much better bound needs even more theory and more work, and sometimes people write papers or books on finding bounds for these sums, or something, not understanding the sum, something in mathematics. So this is a nice sum here, a bound for the sum, if there is a bound, other than that, like if you might say, okay, so what happens if I have 1 over n? Well, 1 over n, this is infinite, that's infinite. So it says that s is bigger than infinite and less than infinite, so it's infinite, in fact. So this happened, this makes sense if this integral is finite, or let's say this is convergent. So this really works for convergent series. Otherwise, if that's infinite, then the other one is also infinite, so nothing happens. Nothing really interesting. So, and also let me write something called the remainder, estimate on the remainder. Okay, estimate on the remainder is this. What is the remainder? Rn is in fact sigma, and from 1 hour, let's say k from 1 to infinity, and let's assume that it is 1 to infinity, say a k minus sigma k from 1 to n ak. So what is this? If I subtract this, then it is in fact k from n plus 1 to infinity ak, right? So similar to what I did for a1, starting at a1, you can show that this Rn is in fact Rn, this remainder, is between two integrals, and one is n plus 1 to infinity on this side, and on this side it is n to infinity of x dx. This is also interesting. You can just show this, because this starts at n plus 1, right? It doesn't start at n. So that starts at n plus 1. So it's like this point that was 1, now it is n plus 1. Okay, and 1 before that is n. Say this is n. Right? So remember what I did for that. So if you go this way, you will get this, for example. If you go the other way, you get the other side. So you are basically doing almost the same thing that we started at 1. Okay, so Rn is like this, except it starts at n plus 1, so it goes forward n steps. And the proof, or deriving this formula, is the same. So that is the remainder, and all right. I don't want to go any further into the integral test, except that I said it is basically used for to prove that the P-series test, and so I stop here, and then I will start the comparison tests and the most important ones at the end, which are say the ratio test. Okay, so see you next time.